Okay, good day, ladies and gentlemen. My name is Can Ince, and today I hope to give you a lecture on why insight into the microcirculation and measurement of the microcirculation and quantification of the microcirculation can give you a key insight how to identify hypovolemia and how to administer fluids in critically ill patients. I'm giving this lecture supported by Matthias Hilti, who is my co-worker with whom we have developed several of the concepts that I will be talking about with you today. So first of all, I have a disclosure information. So both Matthias and myself are involved in a company called Active Medical, in which we provide the tools, the micro tools, and the clinical microcirculation products related to the various parameters that I will be discussing today, and this financial relationship I want to disclose to you. So let's immediately start and talk about the physiology, really, of fluids. And if we just look at fluids in the body, we can see here the fluid exchange. Excuse me for the messy slide a little bit, but we can see here that per 24 hours, we approximately have a heart minute volume of 84,000 liters, which is going through the circulation. If we look at what actually then is being transported across the microcirculation to the tissue cells by filtration and absorption, approximately 2 liters goes into the lymphatics, and we see here that a massive amount of water gets transported across the vascular barrier in and out of the tissues. And if we look at the major mechanism by which this occurs, there is filtration and diffusion, and we see that the vast majority of fluid exchange occurs via diffusion. Diffusion meaning concentration difference, and filtration relying on pressure difference. So if we now look at a cartoon of the microcirculation, well, we basically have that on the entrance of the microcirculation, we have a high arteriolar pressure, which is a filtration pressure, which obviously, as it goes down the capillary bed, finally ends up in a much lower pressure, so that the actual pressure of fluids wanting to leave the microcirculation is much higher in the beginning and much lower at the end. However, the osmotic pressure is more or less the same throughout the whole length of the microcirculation. And the osmotic pressure is dependent on the presence of non-diffusible, non-penetratable large molecules, and in plasma, that is albumin. So basically, here we have a cartoon showing what that is, osmosis, and we see here, for example, you have a lot of large molecules and here few. You will see that there will be water transport going through this semi-permeable membrane, resulting in a osmotic difference. So if we now go back to this cartoon, we see that there is an advantage of filtration in the beginning, but an advantage of absorption at the end. So what actually occurs is that what leaves the circulation in the beginning is reabsorbed at the end. And if we look at the sum total of the two, the filtration and the absorption, we actually have a net suction of the fluids from the tissues to the circulation. So when we are trying to replace fluids by what we call volume, which is a very unfortunate concept because it's not volume, it's just volume of fluids, then we see that we basically have two types of solutions. We have colloids and crystalloids. What does this mean? Colloids is the presence of large molecules in a solution. And we have crystalloids, which is basically a salt solution. So the difference between these two is that the colloids exert oncotic or osmotic pressure, whereas the crystalloids don't. And then we also have balanced and unbalanced solution that has to do with pH regulations, which we'll not go into. So the synthetic colloids have gone into a lot of criticism in the last years, actually unwarranted, because the people who use these colloids have really not understood the basic physiology associated with them. And colloids are given when you have hypovolemia. In other words, when you want to ensure that the circulating volume is maintained. And if you give crystalloids, you will give crystalloids and they will just disappear into the tissues and won't support volume. So if hypovolemia is the clinical problem that needs to be solved, colloids are the choice of fluids. They can be albumin. Unfortunately, albumin is not used in clinical practice as a colloid, much more to correct the reduction in albumin levels, which is something completely different than treating hypovolemia. So if we look at the different types of fluids which we have, excellent paper by Paul Frost in the BMJ several years ago. We've got the glucose, the sodium chloride, saline, balanced crystalloids and colloids. And here we see the different compartments which these fluids are meant to target. We can see the colloids, especially for the plasma. Crystalloids will disappear into the interstitial space and lymphatic compartment, as does saline. And if you want to ensure and correct dehydration, intracellular dehydration, you need a solution containing glucose. Otherwise, that fluid will not enter the cells. So, saline balanced crystalloids really only hydrate the interstitial space and are ineffective in correcting plasma volume. So the ultimate purpose, really, of the cardiovascular system is to provide the microcirculation with oxygen-carrying red blood cells and to provide tissue cells with oxygen. So it's not about fluids, it's about oxygen. And fluids do not carry oxygen. Red blood cells do, because it's hemoglobin that is the main carrier of oxygen. So when giving solutions, fluids, we must never forget that if we do this at the expense of diluting hemoglobin, we will have defeated our purpose. Because even though there might be flow of some sort, if that's not carrying any oxygen, then the purpose for resuscitation is missed. So shock is a state in which a circulation is unable to deliver sufficient oxygen to meet the demands of the tissues. So if you want to revert that, you have to provide oxygen in the circulation and improve what is generally called tissue perfusion. But because people can't measure tissue perfusion, there are all sorts of surrogates which are used. For example, blood pressure, filling pressures, venous pressures, pressure. But actually, tissue perfusion is flow, which is something completely different. And if we look at fluid therapy, its prime purpose is to improve microcirculatory blood flow. Not pressure, blood flow. And by increasing the cardiac output, it promotes the exit of flow from the heart to improve the oxygen availability in the tissues by increasing microvascular blood flow. But whether this actually happens or not is uncertain because it can't be measured. So it's key to understand that oxygen content in blood is the dominated factor of oxygen transport. And it is completely and totally determined by the amount of hemoglobin present. So if we give now fluids, which actually dilute hemoglobin, even though we might be promoting flow, or rather velocity, we might be doing it at the expense of oxygen transport. But that's a completely different subject. So if we look at the two different parameters which actually determine the movement of red blood cells and thereby oxygen to the tissues, there are two. It is the convection, which is the number of red blood cells per time in a particular direction, flow, mass transport, but also equally important is the distance between the hemoglobin, the oxygen in the hemoglobin, and the tissues. So in heart failure, we have a normal diffusion with a low convection, but in hemodilution, we can have large diffusion distance due to the dilution of the red blood cells And even though we might have normal convection, the actual diffusion distance might be very large, which would cause dysoxia. So if we apply these concepts now to fluid therapy, we see that in conditions of hypovolemia, in other words, that there are too little circulating volume, here seen on the left, it basically means that the heart is not producing enough output. So if we increase that circulating volume, it will produce more output and it will promote flow in the tissues, and convection will start to improve. However, if we use fluids to this and we increase the flow more and more and more and more, we will finally dilute it and we will get diffusion limited, and that's when we have fluid overload. So the ultimate purpose really of optimization fluid therapy is to have a balance between the convection and the diffusion, and thereby defining the optimal fluid volume. So we did a study to actually look at where does the fluids go in post-ICU cardiac surgery patients. We looked at the cardiac output, we looked at the microcirculation, and using bioimpedance, we looked at the interstitial water and intracellular water. What happened was, indeed, giving fluids increased the cardiac index, but it was at the expense of the microcirculation, which became diluted. As you can see here, all of these vessels with red blood cells disappeared when cardiac index was increased using fluids. And here we saw that the actual weight of the patient increased. Extracellular water went up, but interestingly enough, intracellular went down. In other words, crystalloid resuscitation was resulting in fluids disappearing from the microcirculation to the tissues. And because there was no insufficient glucose in this, was actually extracting water from the cells. And this effect of crystalloid resuscitation causing intracellular dehydration was well known in the 60s, completely forgotten now. And what's so dangerous about intracellular dehydration caused by crystalloid resuscitation is that it causes protein degradation. So, what about the microcirculation and using these concepts to find a resuscitation parameter which could optimize fluid resuscitation? Well, these microcircuitry images that you have shown, led us to develop, together with Matthias, a new point of care tool called MicroTools, which allowed automatic evaluation of all the parameters relating to the microcirculation in this Nature research paper, which we published. Recently, we did a multicentral trial looking at these parameters published in Critical Care Medicine, in which we were actually able to show in a large variety of different disease states the convective and the diffusive parameters relating to various disease states, all automatic. And we showed also which particular parameters were effective in improving the diffusive capacity and which were sensitive to looking at the convective capacity of the microcirculation. But we went one step farther. Because of the high resolution of these images, we're actually able to calculate and observe the capillary hematocrit. So this is a direct measure of the oxygen carrying capacity in the microcirculation. Now, when you give a colloid, what actually happens to this capillary hematocrit is that the distance between these red blood cells increases. That's why people mistakenly think that having to give more blood transfusion with colloid resuscitation has got something to do with chemical aspects of colloids. It doesn't. It basically has to do that it's very, very good at diluting the vasculature because it expands the volume in that. If you give fluids, it just goes out and leaves the capillary hematocrit unchanged. So this capillary hematocrit, which is really the volume of red blood cells in a volume of capillaries, is proving to be a very, very important parameter. If we now look at the speed with which these flows go, we then have a new parameter. So we have called this new parameter, not tissue perfusion, but rather tissue red blood cell perfusion, because it's generally accepted that normalization of tissue perfusion must be the ultimate end goal. However, what exactly it is that's being perfused is unclear. And in this particular idea, we define this parameter as red blood cell perfusion. So what we basically do is we look at the whole field of view, we calculate what the volume is, the intramicrovascular volume, we calculate what the intramicrovascular hemoglobin volume is, and from this, per time unit, we calculate a tissue red blood cell perfusion parameter. So how does this work in practice? Here we have a pig experiment done by Alex Lima and Bülent Ergin. We look microcirculatory underneath the tongue, and we start to hemodilute this animal in much the same way as I showed the cartoon in the beginning. Here you see in the beginning, at the baseline, and here we see later on. Unfortunately, my video isn't working, but you can clearly see that there are a lot less vessels being perfused, and it's going much faster. So even though it's going faster, there are less red blood cells. So what does a tissue red blood cell perfusion look like? Well, here we see that indeed the red blood cells start to go faster and faster and faster. And if we were measuring laser Doppler, we would say, well, tissue perfusion is increasing. But it's the velocity that's increasing. If we now look at the red blood cell velocity here, we indeed see that it increases. But if we look at the tissue red blood cell perfusion, we actually see that it decreases. So despite the fact that the cells are going faster, they're going at the expense of the dilution of the red blood cells, and this parameter is showing that that is not a good resuscitation parameter to actually target. So, ladies and gentlemen, I have told you different types of aspects of fluids, and it must be accepted that the ultimate goal of resuscitation is to improve tissue perfusion. All the guidelines say it. However, what is precisely meant by tissue perfusion is unclear. There are tissue perfusion devices, NIRS, laser Doppler, speckle, but these are all related to parameters which do not directly measure tissue perfusion. Direct observation of the microcirculation allows a direct measurement of the number of red blood cells available in the microcirculation and in the capillaries, and allows a precise and quantitative method to actually quantify and measure these availability of the red blood cells. So we've defined tissue red blood cell perfusion as a parameter which quantitatively measures flow and is generally perceived for increasing red blood cell, for taking convection and diffusion capacity into account. And this can be done automatically by our newly developed MicroTools software platform, which allows, in our opinion, for the first time, a goal-directed parameter for applying fluid therapy in critically ill hypovolemic patients. Thank you very much, ladies.